Okay, so now we got question number 4, and question number 4 pretty much ramps it up. This is where we start to get all of our equations, all of our ideas bundled into one, and where things get more difficult. So with this one, we're saying water of density 1,000 kilograms per meters cubed flows at a speed of 3 meters per second through a section of pipe of radius 0.040 meters. The pipe bends upwards to 0.25 meters above its original height and tapers to a radius of 0.020 meters as shown in the figure to the right and above. The water pressure is 1.5 times 10 to the 5th pascals in the lower part of the pipe. The water pressure in the upper part of the pipe is most nearly something. So again, pause this, try it on your own, and then continue the video when you have an answer and check your work. Okay, so this looks like we're going to have to use conservation of energy for our fluid, which means we're going to have to use Bernoulli's equation. And in this case, we can't cancel anything out. We can't just set anything to 0 because we are changing our height. So we really have this situation 1 over here and situation 2 over here. So I'm going to write out my Bernoulli's equation. It's P1 plus rho g y1 plus 1/2 rho v1 squared equals P2 plus rho g y2 plus 1/2 rho v2 squared. So I'm going to start filling in what I know. I'm not going to write in the density yet because I don't want to write 1,000 a bunch of times. But so I do know the speed at point 1, and I also know that this is kind of my baseline for height. So what I care about when I'm dealing with this height is really my change in height. So how much change in energy do I have? So what I can do is I can say this is at a height of 0, and this height has increased, and it has a corresponding increase in gravitational potential energy per volume. But so that kind of helps out a little bit. I can call this 0, and I can plug in my V1. And I also know the pressure at this point 1. I know it's a 1.5 times 10 to the 5th pascal, so I'm going to fill that in. Maybe I will write 1,000. I'm feeling crazy. The velocity we said was 3. Plus P2, which is what I want to solve for, plus 1,000. Oops, no, just kidding. And then we see that at point 2 it has an associated height of 0.25 plus 1/2 times 1,000. No, I don't know the velocity at point 2. So I don't know that velocity, but what I do know is that when I'm dealing with anything, especially fluids, we have this conservation of mass. We know that mass is conserved in the flow of a fluid, and that's associated with this conservation in the volume flow rate. So we have this conservation of mass, and our continuity equation is what helps us with this conservation of mass idea. So this conservation, this continuity equation that tells us the volume flow rate is going to be the same throughout the pipe. In some amount of time, the amount of volume of liquid or fluid that we put into the pipe has to equal the amount coming out, because we know that mass has to be conserved. So what we can do is set up this A1 V1 equals A2 V2. We're dealing with circular pipes, so we can say the cross-sectional area at point 1 is going to be pi times the radius 0.04 squared. And then our velocity at point 1 is 3 meters per second. That's pi. We know the radius at the top is 0.02 times V2. So we set up this continuity equation. I can cancel out pi, and I could do ratios, but I'm not smart enough for that. 0.0048 divided by 0.02 squared. V2 is equal to 12. I guess it makes sense because this is doubled, but it's squared, right? 0.04 is 2 times 0.02, but then because we have the square, we have it quadrupled. So it makes sense that our velocity is quadrupled. So now we know V2 is really equal to 12. And then we can plug that in. I'm going to pause this really quick so I don't waste time. Okay, so we got on the left side, I got 154500, and then I got on the right side P2 plus 74450 when I do out this algebra with a calculator, which leaves us with a pressure of 80,050 pascals at this secondary location. It's not. Alright, and then if we're checking to see if this makes sense, let's see. So this velocity term, this one definitely increased. We saw that we went from a velocity of 3 to 12, so we had an increase here. It got bigger. Let me actually, so this is big. This is kind of small. This height, it also increased. So we have something that went up, something that went up, something that's small, which means our pressure over here would have to be a lot greater than it is over here in order to satisfy that conservation. And that's what happened. That checked out. Cool. So that is our answer. If you use 10, you probably got 0.8 times 10 to the 5th pascals. That's just kind of how College Board simplifies it. But yeah.